Hi. Today we're going to be, since last time we did a little bit about convergence and whatnot of sequences, today we're going to discuss not convergence, which is called divergence. A sequence can do one of two things. It can either diverge or converge. It always does one and not the other. So if a sequence doesn't converge, then it diverges. There are a few ways this can happen. A sequence can diverge to infinity, which means for any, you can pick M. We're going to make up a threshold here, we'll call it big M. This can be natural or real, it doesn't matter, but we'll say that it's real. There is some threshold, big N, which is natural, such that for all n bigger than n, we have a n bigger than m. This can be greater than or equal to. So basically we have our xy here. Let's pick some m. And if we have eventually all the terms of the sequence are above this m, and that holds true for any m. So like maybe if I pick this other m, we'll call it m tilde. These terms are not above m tilde, but eventually if I go far enough out, they all are above m tilde. So basically, if any dashed horizontal line I pick eventually has that all terms of the sequence are above that dashed line, then we say our sequence diverges to infinity. Similarly, we can diverge to negative infinity. Pretty much the same thing. For any m in R, there is some threshold n, after which for all n bigger than n, all the an's are less than m. This can also be less than or equal to, doesn't matter. So the same thing, just upside down. If any horizontal line we can pick, eventually all the terms are below that horizontal line, then we say this diverges to negative infinity, or just else. A sequence can diverge, but be bounded. In this case, we just say it diverges. So a sequence can diverge to infinity, to negative infinity, or to neither. Any three can happen, and any three do happen. We can take a look at our definition of convergence that we had to sort of get a grip on sort of what divergence could really mean. Let an be just a sequence and a some real number. Then an converges to a if and only if for any epsilon greater than 0, there is a natural number n such that for all n greater than n, the distance between an and a is less than epsilon. To negate this definition, it's pretty simple. Swap all for alls for there exists and vice versa. So, and negate the final thingy. This will make sense in a second. So literally all we're going to do is we have for any. So we're going to just replace that with there is some epsilon greater than 0. We have there is, so we're going to replace that with such that for all n in n. We have a for all n greater than n, so we're going to replace that with there is some n greater than n such that, and then just the negation of this last thing right here. The negation of this happens to be distance between an and a is greater than or equal to epsilon. So a sequence doesn't converge to a if we can find some epsilon such that for any threshold, there's some element of the sequence past that threshold that's more than epsilon away from a. So whereas here we had to show for regular convergence that any epsilon greater than 0 had a threshold after which all terms were in the epsilon bubble of the supposed limit. We're doing the opposite of that. Well, we're saying, well, that's not true. So there has to be some epsilon greater than 0 such that no matter what, we can always find a term that's epsilon away from 0. It's like, this is the example that he gives in the book. If I had the statement, every university in America has a student that can dunk, what would I need to do to disprove that? I would have to find a university where no students can dunk. That's it. All I have to do is show that some university has no dunking students, and then the claim that all universities have a dunking student is false. For convergence, you want to show for any epsilon greater than 0, some condition holds. For the negation of it, you just want to find some epsilon greater than 0 where it doesn't hold. Great, we're going to get right into an example. See how this actually plays. So we want to show that this sequence converges. an equals -1 to the n. We can draw it. Here's 1. Here's -1. It looks like this. It should be obvious that this doesn't converge because any 2 points next to each other are 2 away, right? So they're not getting closer at all. But let's show that with the definition of divergence. So in order to show that this thing diverges, we're going to suppose we're going to have an acronym here, BWOC. That means by way of contradiction. That means we're going to assume the negation of this and show that that's nonsense. So what does that mean? We're going to actually assume that this thing does converge and then show that that leads to a contradiction. So we're going to suppose that an approaches some a. If a sequence converges, it's got to converge to something. So we're saying that a is that something. Okay. Now our mission, find some epsilon greater than 0 such that for any natural number n, there is some n bigger than n such that the distance between an and a is at least epsilon. Okay, I can find such an epsilon. Let epsilon be 1/2. Okay, since an goes to a, this is the thing we're assuming for the sake of contradiction, there is some n, which is natural, such that for any n bigger than n, the distance between an and a is less than 1/2. There are 2 cases. If n is even, then an is just 1. So that means 1 minus a is less than 1/2. If n is odd, that means -1 minus a is less than 1/2. Okay, and that's if and only if. We're just going to take the negative out of here. 1 plus a is less than 1/2. Okay, then that means, let's draw a little number line here. Boom, boom. So here's 1, and here's -1. We know that the distance between 1 and a is less than 1/2. So here's 0. If we draw a little bubble of radius 1/2, a should be somewhere in here. But we also know that the distance between -1 and a should be less than 1/2. So if we draw the same bubble right here, 1/2, a should be in there. So a is both less than 0 and bigger than 0. This should obviously appear to be nonsense. Okay, this bubble, this 1/2 radius bubble, doesn't contain 0. In fact, the whole thing is to the right of 0. And this bubble over here also doesn't contain 0. The whole thing's to the left. But one real number has to be in both of these. That simply cannot be. Thus, the original assumption is wrong. This sequence diverges. Now, it doesn't diverge to infinity or -infinity, but that's fine. There are sequences that don't diverge to infinity or -infinity, but nonetheless diverge. For example, this one, no problem. We're going to end it with one more proposition. A sequence cannot have more than one limit. It will suffice to show a convergent sequence has one limit. So we're going to suppose, we're going to do this by contradiction again. So we're going to suppose that an approaches a and an approaches b, where a is not equal to b. Okay, so we're saying, well, what if a sequence did have 2 distinct limits? Since a is not b, the distance between a and b is bigger than 0. Okay, either b minus a or a minus b is bigger than 0, and one of those is the distance depending on which one's bigger. Okay, so now take epsilon to be equal to, we're going to say the distance between a and b divided by 2. So what I'm going to do here is we're going to draw our little number line. suppose A is over here and B is over here. We can actually make this over 3 just to be extra careful. So we're going to draw a little bubble around these two where both of these are the distance between A and B divided by 3. Okay, that means this whole thing, that's the distance between A and B. That right there is a third of it, and that right there is another third of it. So there should be another 1/3 of it in here where these bubbles don't touch at all. Since AN approaches A, there is, that's what that backwards capital E is, there is some threshold and lowercase a, I'm going to call it to specify, such that for any n bigger than n, all the terms of AN are within epsilon of A. That means eventually they all get stuck in here. And since AN approaches B, there is some NB, such that for all n greater than NB, all the terms are trapped in the B bubble. So eventually all the terms get trapped in here. Take some big N to be the maximum of the two, NA and B. Then for all n greater than n, the distance between the ANs and the A and the distance between the ANs and the B are both less than epsilon. So eventually every real number is trapped in both this bubble and this bubble, but these bubbles share no numbers. So there can't be any real numbers in both the bubbles, which is a contradiction. And that concludes that proof. Limits of sequences are unique. That's one of the ways to show that 0.9 recurring is equal to 1. It's just one of many.